So COHP stands for crystal orbital Hamilton populations. Yep, Hamilton. Not Hamiltonian, Hamilton. ZOHOP? Oh, you mean X-hop? Or crystal? Xtal?
Yeah.
Okay. This is similar to COHP, but we actually get useful information. Well, we get energetic information out of it. So similar. COHP, but it utilizes, when you see Hamilton relating to Hamiltonian, what type of things do you think it's going to talk about? Matrices? Yeah, well, because we're dealing with quantum, you're going to have matrices. We are going to use the secular equation, yes. And what does that all relate to? Energies, yep. Utilizes energy and the Hamiltonian.
So it's not Hamiltonian, but it is.
Yes. Okay, I have about 3 pages of mathematical derivations to show that this is true. Do you guys want to go through that derivation, or do you want to get to the punchline?
Well, hold on.
Katie, we have not really touched to math, and I feel bad for a while because it's a physics-related thing. What would you like to do? Lily?
I wanted to do the derivation.
I don't care.
I wanted to do
Okay.
Yes.
Yeah, it's just, if you want to just take pictures.
Sure. Actually, maybe I could even ask Richard to go through it. He might do, the inventor of it. So he might do it. Okay. Let's get to the punchline. You have to utilize the secular equation. We talk about something called band energy, and we pop in Hamiltonians. Let me get to what I want. Okay, jumping to the end, which we call E band, will be equal to this summation.
So, are you just going to follow the derivations on Google, or is it going to be?
Probably be a YouTube video. I can get to it. Just H, not H hat in this case. Yes. So this thing is known as the Hamiltonian matrix. That thing, N usually means what for us? Yep, number of states, number of energetic states. If this was the Hamiltonian matrix, and if you remember back, the co-op was related to the DOS times and overlap. What do you think this thing is? Which is also, yes, this is the DOS matrix. And this portion right here, those two things multiplied by one another, that's a co-op. Okay. So now, the cool part to this is We got Hamiltonians, which relates energy. So we can talk about energies in this case.
Is the band energy, okay, you're playing co-op against energy,
Yes.
against band energies, or just energy?
Yeah. This is technically band energy that you're getting here. Slightly different, but slightly similar. So again, COHP tells us about bonding and anti-bonding contributions. But energies too. This is the unfortunate part of things. Okay. And it's not so much a downside if I didn't show you what COHPs were, but I showed you what COHPs were. And most of the community grew up dealing with COHPs. So they get confused by an aspect of this. Okay. A negative. Yeah. Co-op value. What does that mean about the energy? Yep. E is lowering. What does that mean about the interaction? Okay. A positive co-op value. What does that mean? Yep. E is increasing, and it's anti-bonding. This is the opposite of the COHP. So generally, we plot negative COHP.
I feel like having negative co-op is worse than just having it beyond.
Yep. Like if we were trained to start this way, then we wouldn't worry about it. But the community has gotten so attached to this direction being bonding, that direction being anti-bonding. That's what we plot. Okay, let's look at an example for this. We're going to look at a molecular example. I'd give yourself half of a page. Ha! You need some? You could probably squish it. I just like it dispersed a little bit more. Okay, for N2, what's the Lewis structure of N2?
It is the triple bond, got lone pair, and one on.
Yep.
What's the Lewis structure of next?
I don't want to talk about it.
I missed this joke. Bring this back.
No.
I like it too. Okay, Joe, you can tell yellow and blue apart, right? Pretty easily?
Yeah.
Okay. And then on the edges, what color could I use on the edges for the lone pairs? Red?
Yeah.
Okay.
Wait for a second.
Yes.
Yes, we.
Literally just over here.
Oh, I know.
It goes faster.
I argue colors with my wife all the time. It's fun. Actually, as an elementary school teacher, she wrote the color on everything because that way she knew she wasn't wrong when she was telling students colors. She can't tell orange and yellow in red. Yeah, I'd say so. She's partially colorblind. Like she thinks things are purple when they're brown.
That would be really sucky for an element.
Oh yeah, it was. So that's why she wrote literally the color of everything on there, so she would know. Yeah, exactly. Well, and that's where, like, for a while, she was like, "My car is purple." I'm like, "Your car is old lady brown." Like,
Honestly, chocolate cars sound pretty
yeah, I need a purple.
Yeah, oh, absolutely.
Pink is the best color to eat.
Magenta.
I know we already had this argument at one point.
I am partial to greens. That's
Yes.
No,
Mhm.
green's at the
Green is the
bottom.
best color.
No, green's is the way color.
green, orange, black, three of those colors. Blanket statement, bells.
Blanket statement.
Orange was up, but black was down.
Black literally goes with
Oh.
everything.
We should plot. Yeah, we'll leave it alone for now. Okay, if we do the projected densities of states for these things, I got to get my colors right because they're different from what I have in here. Yeah, this is a sigma bond, right?
Yes.
Okay, so we got to plot out the sigma bond here and here. What orbitals make up that sigma bond? 2s and, okay, we'll do 2px.
Should we define what X, Y, and Z is?
Nah, we're all right. Okay, what other things do we have to deal with? Mhm. Colors. Yep, we need the pi bonds. Okay. One here, and what states make up those? 2py, and what else? Yep. Okay, the lone pairs are actually made up of the same stuff as the sigma. And if you plot those out, whoop, they're right there.
On like a daily problem
Mhm.
or a example, you expect us to know where we should go.
No, like this is from the calculation. If you draw it out and it's what I would expect, that's okay. Now, what we're going to do quickly is plot this out. Okay, this section, bonding or anti-bonding? Yep, bonding. That guy up top here, the yellow line. Anti. The p orbitals. This one. Bonding, yep. Sorry, should I draw that? Draw that a little smaller. Okay, what about that guy? Yep. So there's our pi star, our pi, sigma star, sigma. What about the lone pairs?
Sigma star is on bottom.
That's a sigma, yeah. Not a sigma star, I'm sorry. What about the lone pairs? Non-bonding, do they show up here?
No.
Nope, don't show up. Okay, if we look at the Fermi level, gotta get my colors right again. If we integrate up to the Fermi level for these types of interactions, we get a total strength associated with that interaction. So the integrated COHP, sometimes just shortened to I COHP, is 14.4 EV 10.1 EV. So this is for which interaction? This one? Okay, what does this tell us about the bond strength?
Sigma is stronger.
Yep. So sigma is stronger than pi.
So could you not connect the lines on the
In this case, we're not doing it because it's a molecular system, not a periodic system. Okay?
But in a periodic system, you have to do a 1D and or a 1D and chain.
Yes.
We would start connecting stuff.
Yes.
Would be sigma to sigma, pi to pi, or just connect everything?
You would really only plot like the sigma interaction, so you'd have to pick one of the orbitals to go with. Okay? All right. This matches logic, right? Okay.
It was a 3D system.
We're not going to talk about a 3D system right yet, but you will be plotting stuff next week associated with 3D systems.
The pi
Mm-hmm.
are the ones shorter than this?
Yes, they are shorter than the sigma
Why?
because they're less of a interaction there. They're a weaker bond.
So they just are.
Yep. I mean, it has to also deal with like the orbital overlap here. Does that make sense? Okay. All right, we got to let the mathematicians in the room.